Hey guys, we're going to be talking about section 5.2, logarithmic integration. So last time we talked about using the natural log to take a derivative, the different rules involved in doing that, and ways to use things like u-substitution from chapter 4 in order to take better derivatives and solve problems that didn't look like they would be solvable by standard methods very easily. And so with today, we're going to be talking about the opposite of that, of course, which is integration. So just like with all functions, if you can if you can take a derivative of a function, you can integrate that same function, and it offers the way to go back and forth. Starting with our first theorem, theorem 5.5. So let's get started. So theorem 5.5 offers us a quick way in order to integrate a function. So note the two parts of theorem 5.5. Part 1, you have the integral of 1 over x dx equals the natural log of the absolute value of x plus c. So for this one, we're dealing with an indefinite integral. Notice we have no boundaries. So not doing an area problem just yet. We're just talking about how to take those basic integrations. Important things to note here are the big details. First of all, as with all things, don't forget the constant of integration. If you fail to put the constant of integration, it is wrong. And secondly, these will produce absolute values. Now, for some functions, it won't matter as much, but for these functions, you need those absolute values when you write it down. It's better to have them and not need them than to need them and not have them. The second part of theorem 5.5 is involving a u-substitution. So this allows us to take a derivative or an integral of a more advanced function, assuming that we can force it to be in this form of 1 over u du. And so we could make u equal to a different function, and we can use properties of integrals in order to take out things like constants or split functions apart, so we can actually solve these kinds of problems. Now, I did have a recommendation from some students that rather than doing the pieces and problems from the text over again, to instead do some of the homework problems, just do the evens, so they could look at both. That way I'm not, limiting how many things they can see. So rather than doing example number 1 with you, I'm going to actually skip ahead and do problem number 2 from this nice homework assignment. So let's go to the homework. And we're going to use this homework to talk about how to use the log rules to take and integrate a basic function. So let's look at problem number 2. Problem number 2 states we have the integral of 10 over x dx. Okay, if I can somehow get it to be in this form, I could take the integral and be done. Now to do that, I'm going to use a property of integration. So I can take the 10 and move it to the outside. Since 10 is a constant being multiplied to the top of this fraction, this becomes 10 times the integral of 1 over x dx. Now the integral of 1 over x dx, according to theorem 5.5, is the natural log of the absolute value of x. So I'd have 10 times. The integral becomes the natural log of the absolute value plus c. This is one way to write it. There's actually another way, because multiplying by 10 is equivalent to having a power of 10. And so this is also considered an acceptable answer. Both are fine. However, you should be able to do both given the context of the problem. And then when you're looking at things like an AP exam, it's possible this answer is on there and this answer isn't, especially if it's multiple choice. So do note that for these kinds of problems, when you have multiple ways of viewing them, the farther you can go, the better you are. Let's go ahead and take a look at number 4 for the same reason. It has the integral of 1 over x minus 5 dx. Okay, this time I'm going to use a u-substitution to solve this problem. The u I'm going to choose u is equal to x minus 5. Now remember, in order to do a u-substitution, I need to plug in a u, which gets rid of the x, and a du to get rid of the dx. So I take the derivative of u and get du. I take the derivative of x minus 5 and get dx, meaning I can now write this problem as the integral of 1 over u du. So in this case, my u is my x minus 5. My du is equal to dx. And now I can integrate using theorem 5.5. According to theorem 5.5, this is equal to the natural log of the absolute value of u plus c. And because we know what u is, according to this function, we can now substitute back in the natural log of the absolute value of x minus 5 plus c. There's no number out front. There's no way to split this apart or change it. This is an acceptable answer. And so you can see I can use theorem 5.5 to simplify these kinds of problems. And the more advanced the problems, the more difficult it is to do this. Now, the better way is just by more advanced u-substitutions. So let's take a look now at number 8. This is similar to example number 3 in your textbook. So in example number 8 from your homework, we have the integral of x squared times, divided by 5 minus x cubed dx. Okay, so this is not in the form of 1 over x, nor is in the form of 1 over u yet. But an important thing to note here, furthermore, it's also not one of the standard techniques. There's no special way I could fix this using a trig substitution, or if I go back and look at my power rules for all the different integrals I have, like this isn't in my standard list, nor can I like split this apart into 2 integrals because the subtraction's on the bottom. Like there's all kinds of tricks you can use algebraically to try to fix an integral. This is one where the best option is to do a u substitution. In this case, the u I'm going to choose is 5 minus x cubed. When I choose 5 minus x cubed, I also need to know what du is. So du is going to be equal to negative 3x squared dx. Now, I don't necessarily have negative 3x squared dx. I do have x squared dx. So what I'm going to do is I'm going to move that negative 3 over by division. So I do negative 1/3 du equals x squared dx. And now I can perform a substitution. Everywhere there is an x squared dx, I can replace it with negative 1/3 du. Everywhere there is a 5 minus x cubed, I can replace it with u. This becomes the integral of 1 over u times negative 1/3 du. I can now move that negative 1/3 to the outside, which is what I'll do. And now I can use theorem 5.5. With theorem 5.5, this becomes negative 1/3 times the natural log of u plus c. And then from here, I know u, according to my idea over here, u is equal to 5 minus x cubed. So this is equal to negative 1/3 the natural log of absolute value of 5 minus x cubed plus c. The hardest thing to keep track of is going to be things like anytime you're dealing with these kinds of functions, dropping the absolute values is going to be second nature. It's going to be really hard to keep track of those, so make sure you keep track of those absolute values. A secondary acceptable answer would be to move that negative 1/3 as a power. So this would become the natural log, the absolute value of 5 minus x cubed to negative 1/3 power plus c. So be sure you're capable of doing both parts, because both parts are acceptable. And again, if you're taking a multiple choice test, this may be an answer and this may not be an answer. So you have to be very careful and know which is which and that both are considered acceptable. So far, okay? I also do number 10 real quick just to showcase one more substitution, because I know we haven't had a lot of practice with the u substitutions and we learned about those last chapter. So let's take a look at number 10 as well. On number 10, we have the integral of x squared minus 2x over x cubed minus 3x squared dx. Just like before, it's helpful to look at a problem like this and decide upon a u. We know from theorem 5.5 up here that if we can get it of the form 1 over u, we can do a simple integration using theorem 5.5. So notice how I'm choosing the denominator to always be x cubed minus 3x squared. I want to consistently choose the one that's going to match this theorem. When I choose that one, I need to also find du. Du would be 3x squared minus 6x. You might notice that these two are not the same. However, they are very close. Just like before, how we can group these two terms together into one thing, this is very, very close to being the correct term. Only problem is, this is x squared, this is 3x squared. This is minus 2x, this is minus 6x. If I was to, for example, factor a 3 out, well, now these two match. The problem is I have a 3 there that I don't want. I can move the 3 over and do 1/3 du equals x squared minus 2x dx. And now these two actually match. Doing a substitution. Integral 1 over u times 1/3 du. And now I take the 1/3 out and perform the integration using theorem 5.5. So 1 over u becomes the natural log of the absolute value of u plus c, which becomes 1/3 natural log absolute value of x cubed minus 3x squared plus c. That's considered one acceptable answer. The other one, of course, would be to move the power up. As a second acceptable answer. So these are the first kinds of problems you're going to be dealing with, ones where you have to perform theorem 5.5 all the way to the fullest. Now, there is a secondary type, which is a little bit tougher to deal with. These are ones where it's helpful to rewrite them using log rules first, and then choosing very strategically on how you wish to work through them. So for your notes, so when it comes to these kinds of problems, in general, you want to choose always u in the denominator. Notice I didn't say the whole denominator here, I just said in the denominator. Because there is a chance that depending on how you choose your u, my goal is to eventually get to one of these two forms. Usually the second one. Because for a lot of these problems, you're going to be forced to use a u in order to get it into this form. That's one of those tricks you got to know. You got to be able to look at this thing and say, where in the denominator can I find? And specifically look to say, how can I use my du and my dx together to fix this problem? Because I know if I choose my u, I'm going to get a specific du from it. So I can choose strategically how I pick my u so that I get something that's going to match with my dx. So just like on this one, like, could I have chosen just x cubed? Yeah. Would it have made the problem easier? No. Choosing both components together makes this better. In this example here, could I have chosen just x cubed? Yes, but it wouldn't have made the problem any better. Could I have chosen 5 minus x cubed? Yes. Could I have chosen x squared? Yes. But only one of those is solvable into one of these forms. And so you have to be able to look at a problem like this and say, is there, for example, something I could choose to be u whose du is in the problem? So this one, if I look at this thing, I see right away I have an x cubed that I know I can differentiate. The 5 is going to go away, and the derivative of x cubed is x squared. So I know I'm going to have those pieces there so I can eventually fix this problem using u-substitution. And so it's about being strategic in how you choose your u. Let's look at number 22 as a good example before we go on. So on 22, the problem we have is going to be the integral of 1 over x ln of x cubed dx. I love looking at problems like these, but I enjoy more spending time and saying, what does this thing actually look like? So let's take a look at this kind of function, and I'm actually going to use Desmos here because I enjoy seeing what this thing kind of looks like. So I'm going to take a look at 1 over x ln of x cubed. So if you've not seen this function before, here's kind of an idea of what this looks like. Boom. This is 1 over x ln of x cubed. Now, with this kind of problem, like seeing the picture doesn't really help all that much, but it does give an idea that this function is not going to be an easy one to integrate because it's got some asymptotes and stuff going on. So let's talk about how to do it. First things first, I need to decide upon a u, right? And I want to look for a specific u whose derivative is in the problem already. So in this case, I have some options. I could choose x, but the derivative of x is 1, and I won't have gotten rid of the nastiest thing, which is ln of x cubed. I could also choose this entire thing. However, if I choose the entire thing, I'd have a derivative which has a product in it, with a chain inside that product. That's not looking so good. I could just choose ln of x cubed, so I could just choose this piece. But now I have a chain, and the derivative of that chain isn't in the problem. And so it turns out, one of the best things you can do is to rewrite first. Powers become multiplication problems. So the power of 3, which is inside the natural log, moves outside the natural log as a multiplication problem, meaning it also moves outside of the integral. And as weird as this may sound, these two are actually equivalent. Let's take a look. Turn this back on. We come over here, 1 over 3x ln of x. Yeah, they're exactly the same. But one of these is much easier to integrate because of how I can choose my u. Now I can choose a very specific u equals ln of x. Why on earth would I choose u equals ln of x? Well, for one very specific reason. What's du? Du would be 1 over x dx, and look what I have. I have 1 over x and dx in the problem. So I'm choosing a very specific u because its du is in the problem. You always want to try to choose a u whose du is in the problem if possible. So once I've done this as my u, notice how the problem changes. So I still have the 1/3 out front because I haven't done anything to it. Integral. So the 1 over the x and the dx are both going to be replaced with du. However, we still have 1 over ln of x, and ln of x, remember, is now u. So we end up with this function instead. Much easier to integrate. In fact, it's the exact property of theorem 5.5 part 2. So let's integrate. 1/3 ln absolute value of u plus c. Everywhere there's a u, I replace with the natural log of x. So this is equivalent to 1/3 natural log of the absolute value of the natural log of x plus c. And that's the answer. Notice how we have to first recognize that the function we have is not a good function to integrate. We then have to look at it and say, well, maybe there's some rules I can use to simplify this, to rewrite this. I could have also moved the 3 to a power, because again, it's being multiplied, but that doesn't make it any easier. Moving the 3 out does make it easier, because I can then choose a very specific u to allow me to integrate this function. And notice I chose this u because its du was in the problem. That's a huge step, one that takes practice, and why you're doing these homework problems, is you cannot pick the u easily unless you're used to seeing a problem like this and going, if I choose ln of x, then my du is 1 over x, and I have it. Tricky, tricky, but there it is. Okay. Next, I want to talk about the area type problems. So these have all been indefinite integrals, which is great. Now I want to talk about one of the ones that involves a definite integral. So let's take a look at the problems. Now with definite integrals, you don't really change anything. You're still doing the same basic problems. It's just now you have to plug in the limits and actually get a solution. Let's look at number 74. So I go to my homework, scroll down. number 74. Here we go. Find the area of the given region. Use a graphic utility to verify your results. Cool. I'm going to zoom in a little bit, make it a little easier to see. There we go. So remember, in order to write this as an integral, let's take a look at the function. First, what are the boundaries? Well, the boundaries are 2 and 4. They're where the x values start and where the x values stop. Next, the function. 2 over x ln of x. Notice why I chose this one is because it looks really similar to the last one. Okay? And we're doing it with respect to x. So let's take a look at this function. So first thing first, I'll remove the 2 outside. Okay, and now just like before, I'm going to choose a specific u whose du is in the problem. There's my du, and there's my u. Okay, let's rewrite. So the 2 is still up front. Integral from 2 to 4. Now remember, these are x equals 2 and x equals 4. 1 over u du. Okay, next. Let's actually integrate this. So according to our substitution, we'd use theorem 5.5 part 2. This becomes natural log, the absolute value of u, evaluated from x equals 2 and x equals 4. Now I plug in the u as an x, so that way I can actually evaluate ln of the absolute value of ln of x, evaluated from 2 to 4. And then I just plug in and get an answer. So from here, I would get ln absolute value, ln of 4, minus ln absolute value, ln of 2. Now, in these kinds of problems, you can either leave it here. You could pull out a calculator, which is, if I'll be honest, it's probably what I would do. I don't want to have to sit here and try to figure out what that answer is. So I'm going to type in ln of 4 minus ln 2. And I get an answer of 0.6931. Now, I can verify that result using my TI-84 or any other graphing calculator that you have. And for mine, I'd have to do it on my phone. But we should be able to plug in this integral and get the same result. Now, quick side note here. We chose to leave everything in terms of x and solve it in terms of x. But whenever you do a u-substitution, you have the option to change the entire problem into u's. And so let's show what that looks like real quick. I could have changed this entire function to be 2 integral 1 over u du. But I can actually change these boundaries, because if x equals 2, that also tells me what u equals. If x equals 2, then u equals ln of 2. If x equals 4, then u equals ln of 4. And you can quickly see that this will get the exact same result just by looking at the integral. So you'd have a 2 out front. Wait a minute. Wait 1 minute. There should be a 2 here. How could I drop the 2? This should be 2 times all of this. So it should be 2 times that, which is 1.3862. Okay. Stupid Douglas. Making mistakes. Okay. So up here, I can clearly see that I'm going to get the exact same result, because when I plug in for u, I'm going to get ln absolute value of u evaluated from ln of 2 to ln of 4 with the 2 out front. And you can see eventually it will get right back where we started. It's just I don't have to remember to plug back in x, which can be annoying. And so there are many ways to do these kinds of problems. You kind of have to just find one that you're comfortable with and kind of work your way through it. And if I do my graphing utility, I should get the exact same result. And to do that, I'm going to use Wolfram Alpha. So I go to my computer. So here's my Wolfram Alpha. Make sure it matches my original problem. Try that. There we go. Looks like I may have had a small rounding error, but that's good enough for me. So there we have it. Pretty neat. And so with these integration rules, we can do all kinds of nifty and fancy stuff with them. Okay. Next thing I want to talk about is something from algebra. Simplifying using division first. There comes a time where, depending on the problem you're looking at, it is impossible to pick a u whose du is in the problem. If you look up here at an example like number 16, let me zoom in a little bit. We'll actually be doing 16 here in a moment. If I choose the x minus 2 in the denominator to be my u, well, then the top is, it's nasty. And solving it would not be easy. So one of the things you can do is use a property of trig, a property of college algebra, and a property of algebra 2 to try to simplify this thing first. So let's take a look at number 16. I'm going to showcase on number 16 how you can simplify using division first. We have the integral of, let's see, 16 2x squared plus 7x minus 3 over x minus 2 dx. Okay, so first thing to note here, big detail, if I choose any of these to be u, it doesn't work out. Now you might look at this and be like, what if I choose the top equal to u? Well, here's the thing, the bottom is in the denominator. Like if I choose like u is equal to 2x squared plus 7x minus 3, I end up with du equals 4x plus 7, and that looks promising. However, notice that it's 4x plus 7, not x minus 2. Notice that I can't factor this to become x minus 2. No matter how creative you get, there's no number you can just pull out of this and it makes it x minus 2. And furthermore, this would be 4x plus 7 dx, where they're being multiplied on top, whereas this is x minus 2 and dx on bottom. So these two cannot work. And furthermore, if I choose the u equal to x minus 2 and my du equal to dx, like that doesn't work either, because if I choose that, then I end up with a u on bottom and a bunch of x's on top. I don't end up any easier. And so this is also a bad choice. Instead, what I'm going to do is a basic property of algebra. I'm going to actually divide 2x squared plus 7x minus 3 by x minus 2. This is referred to in mathematics as long division. This was done in Algebra 2 and as well as in college algebra. Long division is when you take a function and you divide it directly. You do it by dividing it in much the same way that you would for your standard numbers. So for example, if I want to turn x into 2x squared, I have to use a 2x, creating 2x squared minus 4x. I then would have to subtract, leaving me with 11x minus 3. The thing about these kinds of problems is that you're always going to end up with some leftovers. So 11x minus 22, switch the signs, to put 19. And so this integral becomes the integral of 2x plus 11, so this is the top piece, goes directly into the problem, plus 19 over x minus 2. Notice the 19 is here, and it goes up here. The 2x plus 11 is there, dx. Now I can use the theorem. I can integrate the 2x and the 11 directly. The integral of 2x is just x squared. Oops. 2x becomes x squared. The integral of 11 becomes 11x. The 19 is being multiplied. Since it's on bottom, it becomes a natural log. And then, of course, the plus c. It becomes an entirely different problem that is much easier to integrate. Now, getting it there involves a difficult step. You have to be able to divide functions. This is not required on every problem. It's only required on specific problems where your u's all fail. If you find that you try to pick a u and it's just not working, you may end up having to do it here. A few hints on this. First big hint, first huge hint is if your denominator is lower degree than the numerator. So notice on this problem we have x squared on top, whereas on bottom we have just x. The top has a higher degree than the bottom. It's probably a good indication you need to take this step. This is usually a good call. Even if they're even, you might consider it. So if I look at this problem, if I look at this list, 18, prime candidate. 20, prime candidate. Because again, the top degree is higher than the bottom degree. Alternatively, you may end up having to do some algebraic simplification, like on 14, where you have to distribute the x into the problem, and then take the derivative to see if they actually match. If you do not get du to appear in the problem, you might consider doing it this way. It is always an option. If you don't like doing long division, you always have the option to do things like synthetic division. But if you don't remember how to do synthetic division, then I would not suggest just trying to learn it just for this process. If you don't remember how to do synthetic division, then don't try to relearn it just to do this process. Like, it doesn't work. And don't forget, once you're finished getting the long division done, you still have to integrate. And so you still have to integrate the 2x. You still have to integrate the 11. You still have to integrate this piece, which, if you do it properly, this piece will always turn into a natural log. And then finally, don't forget your plus c, because these are indefinite integrals. These are interesting and kind of strange problems. So always look to them as an option for how you can approach what you're going to be doing next. But there it is. If I look at this problem and look at something like number 18, same basic way. Leave 16 up here as kind of a guide. So number 18. We have the integral of x cubed minus 6x minus 20 over x plus 5 dx. I see here my bottom has a lower degree than my top. So this is a prime candidate to do integration by using a long division first. Now, if I was to choose some u's, like let's say I was to choose the bottom to be u, it doesn't work. If I choose the top to be u, it doesn't work. Try them, okay? I can only tell you a few times. If you don't believe that there's a better way, try it and see if you can get to an answer. Because I guarantee you, if you try to force u to be in this problem, you will spend half an hour to an hour trying to get this thing to work out. It isn't pretty. Just try it this way. Okay. Next, once I've got these pieces, I'm now going to do a division problem. I have x cubed. The big thing about doing these kinds of division problems is remembering that every term needs to have a piece in this division problem. So like I have 0x squareds, so I need to include them in my division. Then minus 6x minus 20, otherwise you're likely to get a bad result. And then of course x plus 5. I want to get these to match, so I use x squared. X squared times x is x cubed. X squared times 5x is 5x squared. Flip the sign. Doing your basic long division. If you don't remember how to do long division, it's just you look it up. Or you might go and see if there's any videos online that could help. And there's also some examples in text. So then we do minus 5x. So minus 5x squared minus 25x. Flip the signs. This becomes 19x minus 20. And then to get these to match, I do plus 19. So 19x plus 95. Double negative. This becomes negative 115. So this integral becomes the integral of x squared minus 5x plus 19 minus 115 over x plus 5 dx. Is this process annoying? Yes, very, 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 very annoying. But does it get me to a function that can now be integrated? Yes, because I can choose a simple u, x plus 5, fix this one, and the other three pieces can all be integrated directly. This first piece becomes 1/3 x cubed. The second piece becomes 5/2 x squared. Remember, add 1 to the power and then divide by the new power. Plus 19x. And then minus 115 natural log of x plus 5 plus c. If you can divide, the solution you get, you can always integrate. But the question becomes, can you divide? Again, there's some great examples of this in your text. Zoom in out a little bit. What the hell's happening? Okay, weird. Let's see. There's some great examples of using this right here, example 5. If you're still having trouble understanding where this piece comes from, use example 5 to kind of help you out. It's really helpful. Okay, next thing for your notes. After all of this, the next thing I'd recommend you have for your notes is this box right here. If you wish to know how to integrate, because this is kind of the last major integration we have one last piece left before we finish the year. This is a big finish though. So, number 1, learn a basic list of integration formulas. So these include all your power log rules, your trigonometric rules, your basic rules from section 5.7. Like, I can't stress enough, know your basics. Number 2, find a formula that represents all or part, and you can often use trial by error to do this. This way you can make your u so that it conforms to the formula. If you can't find a formula or a u that works, try altering the integrand. Notice how we haven't ordered this. First try your basics, then see if you can find a u. If not, then see if you can rewrite it. There's also some trig identities we're going to talk about, and division identities. And then finally, if you have a process or software, like you have the TI-84s perhaps, that can do it for you, or Desmos or Wolfram can also do it too, then use that software to help find it the other way. Now, at this point, we're going to go here, integrals of trig functions. So, when it comes to integration, one of the ways you can do an integral is in fact using trigonometric functions. Now, if you're going to do it by hand, what the heck's happening? I'm getting a weird error box. Okay, here are some that you can know. Now notice that for each one of these, it has a u inside of it. So it means that inside that sine function could be something more complex. Okay, inside of that sine function, there could be some kind of more simple function. And so when you look at these kinds of problems, make sure you have a function. What the heck is that? Make sure when you look at these functions, you can integrate just sine into cosine. You can integrate tangent into a natural log, secant into a natural log, sine or cosine into sine, cotangent into a natural log, cosecant into a natural log. But if there's something more complex inside of it, then you may have to do a u-substitution first. Let's look at an example. Let's look at 38. So you can either use u-substitution indirectly, kind of like how we've been doing previously, or you can kind of do it directly by just using a formula. On 38, we have the integral of cosecant squared theta, cosecant squared t over cotangent t dt. Now, why is this so good? Well, it turns out if we look at this, you might recognize that cotangent has a derivative in the problem. The derivative of cotangent is cosecant squared, which means that I have du already in the problem, and I have u in the problem, meaning I can take this function and rewrite it as 1 over u du. From here, I can use my basic integration rules. Using theorem 5.5, I would get logarithm, natural log, the absolute value of u plus c. And then I know that u is cotangent of t, so this is the natural log of the absolute value of cotangent of t plus c. So you can do your basic substitutions that way, where I use the trig rules to get the solutions as opposed to just the natural logarithm rules. Alternatively, if I look at a problem like, say, 32, I can use u-substitution in an entirely different way. So if we look at 32, I have, sorry, let me get my mouse out of the way, the integral of tangent of 5 theta d theta. Now, if I look at that list that I have an integral for just tangent. It's negative natural log of cosine of u plus c. But I don't have an integral of tangent of 5 theta. So if I could somehow convert that 5 theta into a u, I could then use this integral to find the answer directly by using this integration formula. So here's what I'm going to do. I'm going to force u to be equal to 5 theta. If I do that, my du becomes 5 d theta. Remember, theta in this case is a variable, so when I take a derivative of 5x, I get 5 dx. And as such, when I take a derivative of 5 theta, I get 5 d theta. Now, in this problem, I don't have 5 d theta, I have just the theta. So what I can do is move the 5 over, making it 1/5 du equals d theta. I apologize. And now I can actually integrate. I would have tangent of u times everywhere there's a du, or d theta, I can replace it with 1/5 du. I can move the 1/5 outside using basic integration properties. And now you notice this matches my form. And so now I can use the cheat from the book. The integral of tangent of u is equal to 1/5 times negative log absolute value cosine of u plus c. And then I could simplify this, so I could do negative 1/5 natural log absolute value cosine of, everywhere there's a u, I replace it with 5 theta, so cosine of 5 theta plus c. This is one acceptable answer. I could also move the 1/5 up, but that's all fine. So there we have it. There's 2 different ways we can use these integrations, which means we now have a lot of integration rules. In fact, in just a moment, I'm going to pause the recording, and I'm going to go into the book and showcase all the different possible integration formulas we have talked about so far. So give me a second. Okay. If you look in the back of your textbook, this is on page, what page is it? It is in the appendices. So appendices A21. It's the very back of your textbook. There is this part B of the appendices called integration tables. There are hundreds of these little formulas. I'm not saying you need to memorize all of them, but you should note a few of them. Some of them that are really common include these basic ones. And you notice all the ones from this section appear throughout. So you have sine and cosine, you have tangents, and some of these we haven't talked about yet because you don't talk about them until Calc 2. But this is a good list of all the possible integrations you could ever want to know. If you ever wanted to memorize all of these, like, you'd be better than me. I don't have all these memorized. I have maybe a quarter of these memorized. But it's always back there. And if you have your physical textbook, there actually is in the front and the back, I do believe, shortened versions of these tables with the most common ones. And so these are really useful. There's also some in the textbook, which I'll find here momentarily. Okay. If you look in your textbook on page 385, this is in section 5.7, it's the end of this chapter. This is a full list of every integral you need to know in order to pass your test. Now, some of these, of course, we have not yet gotten to. So this we won't get to. No, we'll get to all of them. We won't get to 5.8. That's the thing. But we will get through all of these. We have, this is section 5.7. We have 4 more sections to go to get here. You need to memorize all 20 of these at some point between now and the time we take our test. It is just the way this section works. You notice we have some of them that we already have talked about. So like you have these ones that came from previous chapters. But you also have your more direct ones, such as when you do like a natural logarithm. And then we have the ones that from the trig section we just talked about. So these ones here. And some more advanced ones, which we'll talk about later. Like, this is a good table to memorize. If you want to know what one of those things is to be great to memorize for this class, this is it. The integration rules are great. There's also a similar one of these in the book for the derivative rules. I believe it's 2 pages earlier, but I could be wrong. They're great to memorize because once you have them memorized, you can always pull those out in the middle of a problem, and it means the problem is that much easier. Because if you can't remember how to take the integral of secant, your best bet is to try to turn it into some kind of u-substitution and eventually get here. But it takes a lot more work to do that than it does just to go the other way. So there it is. That's the last thing I'll leave you with for today. Your homework tonight is page 340/364, 1 through 39, every other odd, 53 through 59 odds, 67 through 73 odds, and then number 90 is a capstone that I'd like you guys to try. I'll be leaving this up so you guys can see it. Hope you guys have a good rest of the night. I'll talk to you guys on Thursday when I post the next assignment. If you have any questions, please message me so that I can get those added for our recording on Saturday. Have a good night. Bye.